We're going to get started. My name is Chandra, and I'll be your session chair. And first talk in the program synthesis session is Mobius, synthesizing relational queries with recursive and invented predicates, and we have Mukund presenting.
Okay. Thank you, Chandra. So, this talk will be about relational query languages. So when I say relational query languages, I want you to think of languages like SQL, relational algebra. We are in OOPSLA, we are in programming language conference, some formalism we might be more comfortable with is probably formula clauses. And there are languages that are based on formula clauses too. Prolog, datalog, unset programming, and so on. Right? This talk really at some level is answers the question how do you synthesize recursive datalog queries. I'll explain what datalog is and why recursion is hard in the next couple of slides. Right? So a datalog program, what you see over there is the canonical datalog 111 program. It's a program that finds strongly connected components in the graph. Right? Are two nodes x and y in the same SC? Yes, they are. Well, two nodes x and y are in the same SC. If there is a path from x to y and there is a path from y to x. When you say there is a path from x to y, there are two cases. There is the base case of the interprocess, which is that there is a direct edge between x and y and there is the same path. There is a path between them, or if there is a transitive step, there is a path between them as well. Fairly straightforward to write. If when you think about database queries, you think about queries in relational algebra, in SQL, these just have a flavor that's more similar to inference rules, if you will. And the meaning of a datalog program is really, let's say that I give you a graph, on a specific graph, the one that you see on the bottom left. The meaning of a database query, or data query is to start with the input tuples. So which pair of nodes is there an edge between? Start those. Keep repeatedly apply these rules that I have written down on the left. Every time you apply the rules, you derive something new. And repeat this process until you hit saturation of some kind, until you hit a fixed point. And so the meaning of a datalog program is really just the fixed point of the rules on the specific table that you're working with. Now, datalog, my own introduction to datalog was through my postdoc advisor, Mayur, who has used it extensively for static analysis. There are dramatic examples of places where it's much easier to write a datalog program. An analysis would take several pages. Gets reduced to a couple of dozen lines of code, right? And beyond that, there are also settings where it's used for knowledge discovery, for discovering, for declarative networking, and so on. And it's not just one of these academic pursuits. There are actually industrial engines devoted to solving datalog programs. Now, when you think about all these languages, the first question that will come to your mind, regardless of the fact that we're in the synthesis talk, is the problem of evaluation. I give you a program, I give you a set of input tuples, what's the output tuple? Lots of papers have been published on this, and it's the focus of a lot of research. Papers are still being published on it, by the way. But what we are interested in this talk really is about the question of synthesis. I give you input-output examples, and can you learn a program that's consistent with the data that I have just provided? Why is this interesting? Well, it's interesting for us in the program synthesis community, well, because we are interested in learning more complicated, more expressive programs. It's interesting for people in AI and machine learning because they want to learn, they want to build agents that can reason. And beyond this, you might want to automatically learn a static analysis, automatically learn network policies, and so on, and this just feels like a foundational problem for all those settings. Now, given that it's a foundational problem, there has been a lot of work on synthesizing relational queries, synthesizing them from data. Despite all of this, there are a few challenges that remain. And I have listed three that stuck out to me at the top of my head over here. The first is about learning recursive and invented about learning programs with recursive and invented predicates. I'll talk about that in a second. And the other two are the usual suspects. How do you learn when your data is large? How do you learn when there's noise? As such, none of that will be the focus of this talk. We are focusing on the problem of recursive and invented predicates. And if you really want to think about this problem if I were to reduce it to its vulgar essence, right? The problem is really, can we learn how to find SECs if one doesn't know how to compute reachability? Lots of papers have attempted to solve this problem. What makes this hard is really questions of how do you know that there's an intermediate concept called a path that you should be looking for? How many such invented predicates do you introduce? What are their schemas? Over here, the path is a relation between two vertices. There's a path from a vertex to another. How do you know that the invented predicate has the same schema as the output relation that you are synthesizing? I'll give you an example of where it gets tricky in a second. How big can the rules get? The example that we saw of SEC, the rules were relatively small, but how do you know how big the rule should be? How many of these rules do you introduce? All of these basically, when those of us in the synthesis community look at a problem, we usually are the first technique that we reach for is some kind of enumeration, right? Or some kind of guided enumeration and so on. All of these things really just mean that enumeration is very hard over here. Most existing systems make some kind of assumptions that the user will tell you how many invented predicates there are, they'll give you a limit on the length of the rule and so on. All of these are really just begging the question, how is the user supposed to know? Right? Here's an example of a query that involves a particularly insidious kind of this kind of scheme, not just predicate invention, but actually schema invention. So let's say that I give you a graph whose edges are colored, and the relation that you want to learn is not reachability, but monochromatic reachability. Is there a path from A to B, all of whose vertices have the same color? And so what you see over here is an example data log program that computes monochromatic reachability. This rule RE over there has this relation path X, Y, C. There's a path from X to Y, all of whose edges have the color C. That's an invented predicate, but that doesn't share its schema with anything else. What we are finally interested in is there a monochromatic path from X to Y? We want to project out, yes, we need to keep track of C, but we are going to project it out eventually, right? And how are we to know that the invented predicate has this additional attribute in it? All right. But that's not all that there is in the title of this talk. The title of this talk says recursive and invented predicates. So let's talk about the non-recursive setting, right? And non-recursive settings, in the non-recursive setting, I claim that invented predicates are not really an issue. And there have been plenty of papers that solve program synthesis. For example, for SQL, several papers, a couple of papers that I've listed over there. And let me try to motivate why it's not an issue at all. So here's a program that computes the grandparent, that finds out if two people are cousins of each other. When are two people cousins? Well, when they share the same grandparent. Just inline it out. You don't need to talk about the grandparent to say that two people are cousins, right? And so the problem is that this notion of this trick of inlining everything doesn't work with recursive queries. How much should you inline? And our observation, really, in this paper is that for a given finite set of input-output examples, a finite unrolling is sufficient. So yes, you'll need infinitely many arbitrarily long rules to actually compute SEC. But for graphs that are sufficiently small, this set of 5 rules is sufficient. And so the question that we ask in this paper is really, if somebody shows you a program like this, can you stare at it long enough and recover the original recursive program? And so the architecture of our system is really to begin with an off-the-shelf non-recursive synthesizer, pass it on to this extrapolation algorithm, and from that we get a possibly recursive program P. And so the main goal of the recursive synthesis process over here is to generalize. And so let's imagine that we are trying to find strongly connected components once again, and the base, the seed non-recursive synthesizer looks at this pattern and finds out, makes a hypothesis about what SECs are. Now we claim that this rule over here is actually somehow an unrolling of some simpler set of rules. The question is, how do we find those patterns? And so the details over here, let me walk over them somewhat quickly. But the idea is that that rule over there doesn't expose any internal structure. It's just a monolithic rule. And so we first decompose it into its Chomsky normal form. And that suddenly forces invented predicates into the system. And it allows us to see the internal structure of the predicate. Now, if this is the same normalized non-recursive query, if these are the unrolling of some recursive program, then some of these predicates must be really doing the same thing. They must be playing the same role, right? So let's just merge the predicates, start merging predicates into equivalence classes. Let's do it on a trial and error basis, right? And so the first trial that we might do is take all of the predicates and lump them together into the same bucket S1. So wherever I see any of those predicates, I will instead write S1. It turns out that a couple of rules disappear after this transformation, and what you end up with magically is the program that computes SEC not just on that graph over there, but on every graph that you might find. Now, of course, it's nice in some way, this whole predicate unification process. There's a theorem we can prove that it strictly generalizes, but it might generalize in bad ways. And so we use some tricks from database systems that's to compute the provenance of tuples. And so we look at all of the bad tuples, we compute their provenance, and figure out ways of basically eliminating them. So for example, there's a graph. Here's a program that doesn't really quite compute SECs well. It ends up computing an undesirable tuple. The problem at this point, but just by looking at why this tuple SEC 3, 5, it says that 3 and 5 were in the same SEC, were generated, is there must be some issue in R1 and R4. And so that allows us to focus on which parts of the merge really caused the issue. And so this overall extrapolation process is kind of this CGIS-like structure. We started the original non-recursive program, normalize it, and then there's a back and forth between a data log solver, in this case Souffle, and a constraint solver Z3, where the constraint solver proposes a unification map, the data log solver checks it. If it goes wrong, then it computes the blame assignments, what part of the merge the unification was bad. And when it succeeds, then we have the final possibly recursive program. We evaluated this whole setup on a set of about 21 synthesis tasks. These covered a range of different recursive patterns, if you will. Transitive closure is an easy pattern to get examples, to get benchmarks out of. Intersection, strongly connected component, path from X to Y and a path from Y to X. And I already talked about monochromatic paths, so schema invention. So all of the benchmarks were some variations of these kinds of things. We compared them to three basically state-of-the-art baselines from inductive logic programming, from program synthesis, evolutionary search, and so on. 21 benchmarks. I have normalized the running time of Mobius to 1. And if you look at the other systems, it's, I forget the exact numbers, but really Mobius is clearly the fastest, right? It's, and it's by the way, notice that the y-axis is on a logarithmic scale, so it's really much faster than the remaining systems. Now, Mobius itself, like I said, was started with a seed non-recursive synthesizer, and then it did something to it. So what's the overhead over EGS? Well, turns out not that much. In fact, even the benchmarks where we don't do very well, we can blame it on the seed synthesizer that we're working off of, not the algorithm that I just presented. Really, the question was, does it improve generalization? The short answer is yes, it does. These graphs look magical, but the fact is that Mobius just discovered the real query. EGS could not, and that's why you see the accuracy of EGS dropping off with larger test graphs. All right, so let me stop over here. I have run out of time, but really the conclusion of this talk was that I just presented a new algorithm to synthesize relational queries, and it can learn queries with recursive and invented predicates. The take-home message of the 5-minute summary of the algorithm is that you start with a seed non-recursive query, normalize it, iteratively unify predicates, use provenance to figure out what went wrong in case something goes wrong, and the unified query is potentially recursive and it gives you opportunities to generalize. We are able to learn several complex patterns of recursive queries and without too much time overhead. Let me stop over here. I'll be happy to take any questions. Thank you.
Hi. This is a very interesting idea. I wanted to know, because you're learning the unruled version over perhaps smaller structures, do you have to choose which solution? I mean, there could be many things that could fit that, and so tons of effort has been spent on similar problems for re-ranking and things like that, right? So is that a problem here, and if not, why not?
It is. Okay. The short version of the answer is that it is a problem. We use the Chomsky normal form. There's all kinds of non-determinism involved in actually constructing the Chomsky normal form. Whatever our implementation chose is what we chose. You are right. And in fact, it is a very interesting problem. So yes, we should talk about that offline. Sure.
Thanks for the talk. You talked about problems of correctness with extra tuples that you don't want, but is your algorithm complete?
So the completeness falls victim to the question that Aditya just mentioned, which is that if, so we are correct, okay, here the short version of correctness is that if there is a solution, we will always produce a solution. Is it the solution the user had in mind? We cannot guarantee that. But yes, the real failing is in my failure to answer his question about what if the Chomsky normal form was not chosen in the best possible way, or the seed non-recursive synthesizer gave us something spurious. The problem is always somebody else, not this algorithm.
Great. Let's thank Mukund one more time.